Building on what we have learned in this chapter, we are now going to model a heatsink. A heatsink is a very common type of device that can be found in many appliances as well as industrial applications, and I'm actually willing to bet that the computer that you are listening to this lecture on has more than one heatsink in it. So basically the idea is that you have something which generates a lot of heat. This might be your CPU, for example, which is placed below the heatsink, and then you have this type of device which jobs basically is to take that heat and distribute it as evenly as possible and to provide as large surface area as possible to exchange the heat with the environment. So usually there's some type of airflow or other fluid flow, depending if this is an air-cooled system or a water-cooled system. So let us assume for now that you have an air-cooled system. So that means that basically a fan blows air through the ribs of that heatsink, and this means that the temperature in the heatsink is getting exchanged with the environment, and the moving fluid, the moving air carries away that heat. And the whole idea, of course, is that whatever device is generating this heat is then kept at an appropriate temperature. Now, really the fundamental physical part here is the large surface area. The larger the surface area, the more energy we can exchange. And this really shouldn't surprise us all that much because we already know that by Fourier's law, basically if there's the temperature gradient, there will be a heat flow. And then of course, the larger the area on which we can apply this heat flow, the more quickly this is going to work. Now, we have to make a couple of modeling assumptions to sort of incorporate this into what we are going to do here. So we are going to assume that the air has constant temperature. This is satisfied, at least to a very good approximation, if you don't consider boundary layer and things like that, if the airstream is fast enough. So if we blow air fast enough through the ribs of our heatsink, then to a very good approximation, we always have fresh air, and the temperature of that fresh air is only raised a very minute amount, and so basically we can make that assumption. And then the second simplifications that we make here is that we model this as a two-dimensional system. So our finite element code is equipped at the moment only to handle two-dimensional systems. So we have to consider that case. But you can see from the picture here that many of these heatsinks, they have a very distinct symmetry. So if you go in the direction into the picture here, then we can see that basically nothing changes. So this is an axis of symmetry, and so we will basically just take a cross section at one point on that axis and use that for the simulation. Now, if we want to simulate this, then the first step is to actually create the geometry as a model. And so we are doing this again with OpenSCAD. So what I want to show you on this slide is how you could model something like this on OpenSCAD. And so basically the idea that I would actually recommend that you all follow is that we first of all start with a square. Okay, so this is going to be our computational domain. So we start from a square, and then we will cut out different things from that square which are not part of the domain that we actually want to run simulation in. So basically we model the heatsink by starting with a solid block of aluminum or whatever material is used, and then cutting out things from there. So our domain in this case is 5 by 1.5. So we have 5 in whatever units you want to measure this in, 5 across the x-axis, we have 1.5 across the y-axis, and on x we go from minus 2.5 to 2.5. So this is how I laid this out, and this is why I have translated this in that particular way. Now, in order to expose the ribs, we now basically have to cut out these air gaps in between, okay? And there actually OpenSCAD gives us a lot of possibility to do this programmatically. So what I will do here is I will actually use a loop, okay? And the loop iteration 0 will have this cutout, loop iteration 1 will have this cutout, 2 will have this one, and so on and so forth. And in that way I can actually create a model where I can programmatically specify how many fins I do have. And you can see here, this is a parameter that we have on the top. Now the loop basically works in the following way. We go from 0 to the number of fins minus 2, so this is the number of cutouts that we have to make. We compute the cutout size. So I think this deserves a little bit of explanation, but basically what we do here is that we take the length of the domain, we subtract the amount of space that the fins need, and here our second parameter comes in, so this is actually the fin size. This basically tells us how the width of the fins that we have here, and this is then the number of space that we need to cut out, and we divide this by how many cutouts we need to make. So this is the size of the cutout, and then we have to compute where the cutout actually starts on the left. We have to start at minus 2.5, so this is the left endpoint of our computational domain, and then we basically advance this by the fin size, so the first cutout starts at the fin size, and then every subsequent cutout will actually start, we will actually be translated both by the cutout size, by the fin size, and then we make the next cutout. And so we do this translation, we cut out a square, and what we then obtain is what I have shown you here. Now, a very important point here is that what we have done here essentially is an example of a parametric design. And by that I mean that we have a design which is not a unique design where we have specified all of the measurements a priori, but we have left some parameters that we can vary in order to increase or decrease certain things. So for example, we could increase the fin width, we could decrease the fin width, we could increase the number of fins, we could decrease the number of fins. And I'm sure if you think about this, you will also have some more ideas how you could add additional parameters in here. And this, I think, is really one of the strengths of OpenSCAD, because it makes it very easily to make such parametric design. Now, why do we care about this? Well, we do care about this because what eventually we want to do is we want to run a simulation. And so one big part of what simulations are used for in practice is to find optimal parameters. So to find how we can vary this parameter such that in this case, for example, the heat dissipation is maximal. And if we have a parametric design, then we can very easily use that parametric design in order to generate different measures, run different simulation, compare the result, and see which parameters are actually need to be varied in order to improve the result, or even to just figure out which parameters are important in order to so what parameters have a big influence on sort of the final temperature distribution that we want to look at. All right, so if we want to do the simulation, then we still have to modify the equation quite a bit. And so the first thing that we need to do here is that we add a source term. So far we have only considered the heat equation without any source term, but in this example we need something that generates heat, okay? And so we don't model this, okay? We don't model all of the intricacies of the device, say the CPU that generates heat. We will just assume that thing has a certain amount of generates a certain amount of heat, and this we will plug into our simulation. And this we do by the source term here. And the source term in some sense is very simple. It basically says we have a fixed amount of heat generation if y is smaller than 0.3, and otherwise it's 0. So basically that means that the bottom part here is heated equally, and then the fins, they are not heated, but they will just conduct the temperature and exchange the temperature with the environment. Now, what does this change in our finite element scheme? Well, the left-hand side as well as the Laplace operator, they remain exactly the same. But now within the weak formulation that we have here, what we do get is essentially the source term multiplied by the test function, and we integrate this over the domain omega. Now, the integral that we have here can be evaluated easily if you think about that. We have on each triangle in our domain, we do have a function, so this function phi j, which is 1 at one corner of the triangle, it's 0 on the other two corners of the triangle. And if you think about this for a moment, I mean, there are many ways to evaluate this integral. You can just write down the functional representations as we did before and compute it explicitly, but you can also just use essentially what is a two-dimensional generalization of the trapezoidal rule, where you take the average of all of the 3 grid points, and then because one grid point gives the value 1 and the other two gives 0, we basically get 1 over 3 times hi. So remember, hi is the area of all of the triangles that are adjacent to the point I, so the point where the ith test function is 1. And so this is the same thing that we have used before on the left hand side in order to do the mass lamping. And then we basically get this, and then the value si, which in our case will be either sigma or 0, depending on where we are in the domain. So putting this all in a matrix formulation, we can do this rather easily. We divide by hi, we then have the time derivative is equal to b times u. So this is as we had it before, exactly as we did before. And then we add the source term, where the source term is just a vector where we put Sn to Snv, and we take 1 over 3. So the hi here cancels. And basically, I mean, this is what we have to add in the code as well. So now we have a function which assembles this matrix B. We now also need a function which assembles this right-hand side, this source term S. And then we can use it in our explicit Euler scheme in a very similar way as we did before. So this should pose no additional complications. What is a little bit more difficult, however, is the boundary conditions. Now, I told you before that we make the assumption that the free streaming fluid is essentially has a constant temperature, right? So room temperature, let's say 25 degrees or 20 degrees. And then in this vein, it's really tempting to impose directly boundary conditions with the temperature of the fluid. Okay, just set the boundary conditions to 25. Now, I encourage you actually to try this out and you run your simulation with that. But the fact of the matter is that this is actually wrong. And the reason for this is wrong because if you would have a constant temperature at the boundary of our computational domain, so if that piece of aluminium which represents our heatsink would have the same temperature as the air, then essentially by Fourier's law, the temperature and the fluid would not exchange any heat. Okay, at the same temperature, there is no physical mechanism which can cause heat exchange. So this is obviously not then what is happening in reality. And so what we need to do in order to make this into a feasible model is we have to somehow model heat transfer across this fluid-solid interface. And because we have there a material interface, what actually happens is that on one side of the interface we might have the fluid which has one temperature, let's say the 20 or 25 degrees, and on the other side of that interface, we have the metal, aluminum, which represents the heatsink. And that actually, even as we approach the boundary, will have a different temperature. Okay, so there will be a discontinuity in temperature across the interface, across the material interface, and this is actually what drives this heat exchange. Okay. So a commonly used model that we are also going to employ here states the following: Q, which is the heat transfer, okay, is equal to H, which is a constant of proportionality, which we call the heat transfer coefficient or the film coefficient, times the temperature of the fluid, the 20 to 25 degrees, minus the temperature of the metal at the boundary. So essentially what it says is that if you have a solid liquid interface, solid fluid interface, then across that interface there is a heat flux which is proportional to the difference in temperature. So if you want, you can sort of look at this as a generalization of Fourier's law in situations where you actually are not in a homogeneous medium, but where you have a material interface. So in our case, we can rewrite this a little bit because we already know that Q, the heat flux, should be equal to the gradient of the temperature, more specifically to the gradient of the temperature pointing across the interface, right? So this is the heat flux that we assume across the interface. So this is the normal vector which points outward, so the unit normal which points outward of the domain, times the gradient is equal to the right hand side here. And so d fluid is just a constant. D is actually what we called U before, so this is what we model, and this is the temperature inside of our heatsink. Now, if you look at this for a moment, you will very quickly realize that these are in fact Robin boundary conditions. So we have a linear combination of the change orthogonal to the interface, to the boundary, plus the function that the temperature at the boundary is equal to some constant value. Okay, so we have to basically impose these Robin boundary conditions in our finite element scheme if we want to model this in an appropriate way. Now, how does this work? Well, Dirichlet boundary conditions is the case that we have considered so far, and usually Dirichlet boundary conditions are imposed as part of the approximation space. Okay. So what by that basically just means that at the boundary you have fixed basis functions. These fixed basis functions have the value that you want your simulation to have at the boundary, okay, and then essentially you just don't change these values if you have time independent boundary conditions, and you evolve this in time, and there's really not a lot that you have to do here. But in some sense, for finite elements, Neumann boundary conditions are actually even more natural. And the reason for this is that the Neumann boundary conditions actually appear directly in the weak formulation. Okay, so let us now discuss for Neumann boundary conditions, because they are really the stepping stone for Robin boundary conditions as well. So let us assume for now we have the condition that the gradient at the boundary is equal to some value which we call B, and then we rederive the weak formulation of our finite element scheme. And for the weak formulation, what we did is we have this Laplace operator applied to U, okay, so the temperature U. We have some test function which we multiplied, and then we integrate over the domain. And then what we did is we did integration by parts, and we used this integration by parts essentially to to basically get one derivative on the test function and one derivative on the solution, and to ensure the symmetry of this operator essentially. And this, what we have here, is exactly what we obtained before. Now, before, for Dirichlet boundary conditions, we made the argument that we can actually choose the test functions with homogeneous Dirichlet boundary conditions, so there's 0 on the boundary, and then that term goes away. But now, since we actually have Neumann boundary conditions, this is no longer true. So we cannot assume that phi is constrained on the boundary. Phi can take any value on the boundary. But on the other hand, we have this term here, which we know the value of, right? So this is just our boundary condition, so we can replace this by b. And then what we get is, we get this integral over the boundary of the value that the boundary conditions fix, times a test function, okay? And then in the discrete setting, we have to integrate this. But this is actually rather easy, because in the discrete setting, in 2 dimensions, the boundary essentially is just a one-dimensional polygon, okay? It's just a one-dimensional curve where basically you have straight lines between each grid points. And then if you want to integrate this, I mean, there are many ways which we can go about this. What I here just did is I assumed that b is constant over the support of the test function, which means I get a bj, and then I have to integrate over the test functions. The integral over the test function is just 1 over 2 times Lj, and Lj is the sum of the lengths of the 2 boundary edges that are actually adjacent to xj. Okay, this is just the length over which the support of these test functions extend. Now you could use maybe more elaborate quadrature rules here, but for our purposes, this is more than efficient. The other thing I really should mention here, this only applies if the point j lies on the boundary, okay? Otherwise, this contribution is just 0. So in the interior of the domain, there is no contribution from this term, but on the boundary, you get some contributions, and this is really what we expect, right? So in essence, we get here an additional source term of a very particular form, and this source term enforces the Neumann boundary conditions. And this really is very, very similar to something that you would obtain, for example, in a finite difference scheme, where you would have some additional term on the right-hand side, which enforces the boundary conditions that you want. Now, so adding this to your code works in exactly the same way as we have discussed before for the source term. There really isn't any additional complication here. But there is still a change in your code that you need to make, because now we don't know the value of ui on the boundary, okay? So previously, for Dirichlet boundary conditions, we did just assume that on the boundary there is a fixed value given. But now this is no longer the case. Now the value of the function at the boundary becomes an unknown itself. And so it has to be treated as any other degree of freedom. So really, in sort of reference to the matrix A, okay, we don't now need to make any distinction between points on the boundary and points in the interior of the domain. We just assemble the matrix for all of them. I mean, points that lie on the boundary might have less triangles that are adjacent to them, but really the algorithm works in exactly the same way as we have explained. So the only real change, and we can see this if we have to go back here to the pseudocode, is really that here we have this if statement, that if the vertex is not on the boundary, then we do this, okay? And otherwise we don't do anything. Otherwise the matrix, the row in the matrix is just 0 and nothing changes. But now we really have to remove this, because now the values at the boundary are advanced as part of the solution. So basically you have to remove this if statement from your code. All right. So this is Neumann boundary conditions, but what we are ultimately after are Roman boundary conditions. But since we did understand the Neumann boundary conditions now, Roman boundary conditions are actually very easy. We once again do the integration by parts. We get this integral, which is over the boundary of the domain. We now replace the gradient of u by what is on the right hand side. Okay, so there's one part which is this constant part that we looked at before. Okay, so this works exactly as on the slide before for Neumann boundary conditions, but now we have this additional term here which depends on the solution itself. Okay, so let us look at this term in a little bit more detail. So we have the integral of the boundary of the solution times the test function. We take the solution as we have always done and expand it in the basis functions. Okay, so then we get this. We have an integral now over the boundary of the basis function phi I times phi j, and now we basically have to evaluate this integral. Now once again, I should say here that if either I or j do not lie on the boundary, there's no contribution from this. And once again, this makes sense because this is really a term which should enforce boundary conditions. So in the interior of the domain, this really doesn't do anything. But on the boundary, so if I is equal to j and if the point lies on the boundary, then we have to compute this integral. Okay, and essentially, once again, this is an integral over the boundary. So this is an integral over the line segments. And so you have to think about this for a moment, but it should become clear very, very quickly how you can evaluate this. Okay, exactly, actually. So there's actually no error here. Okay. So what do we get? Well, if I is equals to j, then we get 1/3 times Lj, and Lj again is the sum of the lengths of these two adjacent line segments. And then if xi and xj are both on the boundary and they are adjacent, so if they're not adjacent, there's once again no contribution, but if they are next to each other, then there's an overlap in the basis function, and we need to integrate out this overlap, and then the overlap basically just becomes 1/6 times the length of the segment. So this is understood as an Euclidean norm. That's just the length between the point xi and the point xj. And now, so I actually was a little bit sloppy here because, of course, what we have written down here, this is only the value of the integral. We still have the sum over ui before, right? And because we have the sum over ui times essentially this coefficient, we actually cannot put this on the right hand side. We cannot include this in the source term, but what we have to do here is we have to include this as part of the matrix. Okay, so what we have derived here, these terms, they actually enter into the matrix and they modify some of the matrix elements here. Now, if you put everything together, so basically this was adding the source term to our numerical simulation, which first of all simulates the creation of heat down there, then adding the part of the Robin boundary conditions to the source term, which does not depend on the solution, and then the third step we have to do is that we modify the matrix according to the part of the Robin boundary conditions that actually depend on the solution. So if we do these three steps, and if we modify our code appropriately, and if we run a simulation like this, then we should get a result like that. And so what you can see basically here, so here there is the heating down there, so there naturally the temperature is the largest. Okay, so it's about 83 degrees. As we go away from them, the temperature drops quite appreciably, and there is some type of heat transfer across the boundary. And now, of course, the design goal is really that we find a heat sink. Okay, we alter the geometry of the heat sink. We vary these parameters in such a way that the maximal temperature that we achieve here goes down, so that this is reduced. Okay. So to that end, those are the exercises that we want to look at. So in 2.4, you will model a heatsink in OpenSCAD and generate a corresponding mesh in GMSH. Now, I already gave you a template for the OpenSCAD code, but I would encourage you to actually think about if there are other parameters that you might consider varying here. Okay, if you can add additional parameters to this design. Then in 2.5, the question is to modify the finite element program to accommodate the source term and drawing boundary conditions. This is basically the 3 steps that we discussed just before. And then finally, we want to simulate this heatsink. I have given you here some reasonable parameters, so source term strength 100, H 0.1, to fluid 25 degrees, but of course you can also play with these parameters and see what happens if you vary them. Now the goal here is really to investigate how the highest temperature that occurs in the heatsink varies as a function of the parameters that determine the heatsink geometry. And of course that's in some sense the important quantity, because most materials, most devices, they have a certain temperature that we can't operate if we exceed that. Okay, so there might be a temperature of 100 degrees or whatever it is. Above that, the device will just not work. Maybe the metal inside will melt or whatever it is. And so if you want to design a good heatsink, the goal really is to design it in such a way that this temperature is reduced. And this is essentially what I ask you to do here. Now, one thing of note, since we are interested here in the steady state temperature distribution, basically you should integrate long enough until you are sure that you are in the steady state. Okay, so maybe just drag the highest temperature, plot this on a graph, and then you can easily see once this approaches the equilibrium. But on the other hand, the initial value is not important here, and so in principle you can choose any initial value, but a fairly reasonable choice would be to just assume that initially the heatsink has a constant temperature of 25 degrees. So at the beginning, basically, before anything happens, the heatsink has 25 degrees, the fluid has 25 degrees, then you switch the thing in, some heat is generated, and the temperature rises until you achieve a steady state.